I want to make a quick correction to the last video where we introduced the carboxylic acid videos. And then we can actually compare them in terms of their relative stability. And that one mistake I did is when I named the ester, all I did is I named kind of the main carbon backbone. I didn't actually tell you how many carbons you have attached to the oxygen over here. Acetate really just refers to this part over here, knowing that it is bonded to, or maybe I should say it refers to this part over here. But you also have to specify how many carbons you have over here. So this molecule that we drew over here is actually methyl acetate. This is methyl acetate, or if you want its systematic name, it's methyl ethanoate. And this is where we get the methyl from. It is methyl. It is methyl ethanoate. Now, with that out of the way, let's actually compare these carboxylic acid derivatives. And I'll compare the derivatives of acetic acid. So the first one we saw was the amide, acetamide. Acetamide looks just like this. This is acetamide. Then the next one we looked at was the ether, and that's the one I just pointed out the mistake on. So this was ethyl acetate. So you have CH3 right here. This is where, sorry, this is methyl acetate. This is where the methyl part comes from. So this is methyl acetate. And then we will compare that to the anhydride version. So this is acetic anhydride. Let me do this in a new color. Acetic anhydride looks like this. Acetic anhydride looks just like that. Acetic anhydride. Acetic anhydride. And finally, we had the acetyl chloride. Acetyl chloride looked just like this. Looked just like this. And of course, these are all derivatives of acetic acid, which we drew at the top of the last video, which is right over there, acetic acid. Now let's think about which of these may or may not be more stable. And to think about it, we're going to think about any resonance structures that these molecules might have. So if we first focus on acetamide, we know that nitrogen forms 3 bonds and then has 2 extra electrons that form another lone pair. And it's actually electron rich because it's a good bit more electronegative than the hydrogens here, and actually even a little bit more, and a reasonably more electronegative than the carbon it's attached to. So you can imagine a situation where a nitrogen could donate an electron to this carbon right over here, and then that carbon can let go of one of the electrons in a double bond with the oxygen, and so it could go back to the oxygen, and you would have a resonance structure. You would have a resonance structure that would look like this. Let me actually use the same colors. You would have a resonance structure that would look like this. This oxygen just gained an electron up there. And actually, let me draw the electron. Well, actually, I'll just put the negative charge due to that electron. And then we had this bond right over here to the nitrogen. But the nitrogen just gave an electron to this carbon right here, the carbonyl, or what was the carbonyl carbon. And so now we have a double bond over here. And the nitrogen just gave an electron, so it now has a positive charge. But this is a resonance structure of acetamine. So pretty stable. Pretty stable. So this is, maybe I should even say quite stable. So this is quite stable. Now, let's think about an ether here. And we could probably do something fairly similar. So if we think about this ether here, oxygen has two extra lone pairs. It is more electronegative than the things that it is bonded to. So it could do a very similar thing to what this nitrogen did. It could give an electron to this carbon right over here, and then that carbon can give back an electron to the carbonyl oxygen, to that oxygen over there. And so its resonance structure would look like this. It would have a resonance structure. So it's almost the exact same thing as what we saw with the amide. So it would have a resonance structure This oxygen just gained an electron. Now we'll have a negative charge. This bond to the oxygen is still there, but this oxygen just gave another electron, formed another bond with what was the carbonyl carbon. It actually forms a new carbonyl group, if you want to view it that way. And so it will look like this. And this oxygen gave away an electron, so now it has a positive charge. So this seems like a pretty good resonance structure. So the question is, which of these two are going to be more stable? And the answer there really just comes out of the periodic table. If you look at nitrogen and oxygen, they're right there. They're both near the top right. They're both pretty electronegative, but oxygen is more electronegative. It is to the right of nitrogen. So because oxygen is more electronegative, remember, electronegativity is just the tendency to hog electrons. How much do you like to hog electrons? Oxygen likes to hog electrons more than nitrogen likes to hog electrons. So it would be less likely, marginally less likely, to give away an electron than nitrogen would be. So this resonance structure is a little bit less likely, or when you think of it probabilistically, it's going to happen a little bit less frequently than this resonance structure. So this one right here, this is going to stabilize it less. So this is going to be a little bit less stable than the amide. So this is, if we call this quite stable, I'll just say this is just stable over here. Now let's think about what's going to happen with the anhydride. The anhydride, once again, we have an oxygen right here. It's got its spare electrons. It's more electronegative than the things that it's bonded to. So it seems like you could do something very similar to what we saw with the actual ether. It could donate an electron. It could donate an electron to this bond right over here, in which case you would have a resonance structure that looks like this. And if it donates an electron to this carbon over here, then an electron can be taken away from the carbon and given back to that oxygen. So that would give us a resonance structure that would look like this. It would give us a resonance structure. That guy now has a negative charge. We now have a double bond to this oxygen. It still has another bond to the other acyl group, just like that. And now this oxygen gave away an electron, so it has a positive charge. So it seems like a very similar situation to what we saw with an ether. But there's another resonance structure here. You could also have a situation where instead of the electron being donated to this carbon bond and that happening, you could have a situation like this, where the electron gets donated to that carbon bond, and then this electron gets taken back by that oxygen. So you would have this situation. You would have a situation where this acyl group still looks the same, bonded to this oxygen, but now we have a double bond over here. This guy took away an electron, so one of the bonds in the double bonds goes away, now has a negative charge, and then you have the rest of the molecule. So you actually have these two resonance structures. So and of course, this is now a positive charge since it gave away an electron. So you might say, hey, more resonance structures, more stability. But the key here is to realize is that both resonance structures are dependent from the same oxygen. They essentially have to share this oxygen's electrons. So each one of these individually is less likely to occur than just what occurs with the ether. This guy's, you could kind of view it as that both of these bonds have to share what in the ether, this one gets it on its own. And we even saw that this is still less likely to occur than this over here. So in this situation, in an anhydride, if one guy's getting the double bond, the other if there's a resonance structure on one side of the anhydride, the other side is still reactive. If there's a resonance structure on the left side, then the right side is still reactive. So we'll call this less stable. This right here is less stable. And then finally, you have your acetyl chloride. In acetyl chloride, there really is no resonance structure here. Chlorine is so electronegative that it is unlikely to give away an electron. It is sitting pretty. It has no, well, I don't want to, but it is sitting pretty with 8 electrons. That's actually true for these other characters right here. But chlorine is very, very unlikely to contribute a resonance structure here. So this gets no stability. So this is the least stable. This is the least stable of the carboxylic acid derivatives that we're looking at. Now, why am I even bothering with all of this, this hierarchy of stability for carboxylic acid derivatives? And I'm bothering with it is because we know, or we don't know quite yet, but I've already shown you some mechanisms that can take us from a carboxylic acid to an ether, or a carboxylic acid to an acyl halide. And in general, you can go between all of these and a carboxylic acid. But since we know their relative stabilities, we know that if you start with an acetyl chloride, you're much more likely to go to an acetamide if you have the proper ingredients there, if you have some amines floating around, than the other way around. You're much more likely to go from that to that, because this is much less stable than that, than you are to go from acetamide to acetyl chloride. Likewise, you're much more likely to go from a carboxylic acid to or let me put it this way, you're much more likely to go from a carboxylic acid to an acetamide. And haven't drawn the carboxylic acid here, but this has better resonance than even its original carboxylic acid than the other way around. Or you're much more likely to go from an anhydride to an ether. So that's why I'm doing this hierarchy. You're much more likely to go from something on the right to something on the left. And we'll explore some of those mechanisms in the next few videos.